Did you hit it? Okay, I'll start then. All right. Dear Heavenly Father, we thank you for this day again, Lord. I thank you for these students. Just pray that you'd guide our thoughts today. Just help us to glorify you in what we do, Lord. In your name I pray. Amen. All right, so we actually say some math today. So we will meet tomorrow, 3:30 to 4:05. All right. So I know it won't be as exciting as what happens before that, but oh well. Okay, so let's talk about trigonometry, trig, and hyperbolic trig calculus. So I actually have a little bit more than calculus on the plate here. What I want to do is just remind you the basic things we know about sine and cosine and their calculus, and also just a little bit about what the big story was in Calculus 1, right? So let's start with that. If you had to summarize Calculus 1 in like 3 minutes, what would you do? You learn two things, right? How to differentiate and how to integrate. What is differentiation about? What's the derivative about? Rate of change, right? So you can draw this picture, the curve goes like this. You take the secant line, you take the point, x, here's x plus h. You remember f prime of x is the limit as h goes to 0 of f of x plus h minus f of x divided by h, right? That was the definition of the limit. It's the limit of the slopes of the secant lines, right? And that describes the rate of change of the function at x. So that's the first big chunk of the course. And then a little bit later we learn integration, right? And integration, what's the problem of integration? Oh, yeah.
Finding the area under a curve.
Finding the area under a curve, very good. So essentially picture something like this, right? And for purposes of, just keeping it simple, say I want to find the area from a to x. We could call this the area function, right? A of x. And our notation for that also was integral from a to x of f of x. Well, I shouldn't really say dx here, right? If I use x for that, I should really use, I'll tell you what, let me, fine. F of x bar and dx bar. I mean, this is a different variable. And so here I'm looking at y equals f of x, right? And something neat happens that connects these two worlds of ideas, right? This fundamental theorem of calculus. And I can explain it to you intuitively, just with a little kind of cheating picture here. If you go on a little bit, right? And you just go here to say x plus dx, right? You can think about this little bit of area that we added, and you could call it dA, right? You could say that's the little bit of area that you add from going to x plus dx. Well, what would be a good approximation to that area? What's the height of the curve here? It's y equals f of x, right? I mean, that is, I'm using x as a fixed variable here, fixed point there. So if the height is f of x, what's the width? Dx, right? So what's the area? F of x dx, right? So what's that say? That says that dA dx is equal to what? F of x. And that's the mystery, the fundamental mystery that relates these two worlds, that the derivative of the area function is the function you're finding the area under. This is bizarre that this happens, but this is why calculus is something we can teach freshmen and why it's not relegated just to experts, right? After you discover this, that integration really is intimately related to reverse differentiation or anti-differentiation, then all of a sudden we can calculate areas under curves that if we took the direct approach, right, in terms of breaking the area up into Riemann sums, it would be fantastically complicated to actually directly compute areas, right? Did you guys use the You define the integral in terms of the limit of the partition getting really, really fine, f of x, change in x and all that. I mean, to actually calculate one of those, even for a simple polynomial, is just horrible, right? But if I, remind you the theorem, and this is of course not a proof, right? What I'm showing you is a sketch. But here's the basic theorem. Integral from a to b of f of x dx is equal to what? It's equal to f of b minus f of a, provided what? What do we need? F prime, big F prime of x equals to what? You guys know this. Come on. 0. No, not 0. I mean, it could be, but...
Isn't it f of a, or f of b minus f of a over b minus a?
No, that would be like an average. Yeah.
If it's continuous?
If what's continuous?
If the function is continuous and it doesn't have
Which function? Like the big F or the little f?
little f.
Little f. Yeah, it definitely helps if little f is continuous, but we could still make sense of it if it was like just piecewise continuous. We'd still be okay. Maybe somebody already said it. I sometimes miss people saying things, but this should be little f of x, right? In other words, big F is the antiderivative of little f, right? It's the antiderivative of the integrand. This we usually call FTC2, Fundamental Theorem of Calculus Part 2. If I teach Calculus 1, I'll spend about 2 days proving this carefully, right? Fundamental Theorem of Calculus Part 1, I gave you a cheat proof of up here. Fundamental Theorem of Calculus Part 1, what's that say? FTC1, it says that the derivative of the area function, right, it's just equal to the function evaluated at the variable bound. This is FTC1. Right. That's a sketch of the proof of FTC1. It's not an actual proof, but okay. So that's everything you learned in Calculus 1. I mean, that's not entirely true. We did some other things with derivatives, right? We talked about increase, decrease, concave up, concave down, how to find mins, maxes, optimize, related rates. We did implicit differentiation. We studied, for integration, we studied methods of integration, right? Linearity, pull constants out, how to integrate a polynomial, how to integrate sine, cosine, exponential, and maybe a few other flavor choices like U substitution, right? So that's where we are right now. That's where we're picking up the story. So with that said, let me turn the page here and talk to you about trigonometry. So what is the trigonometry? I can't spell. Here, fix this. Safe. There. So there's two main players here, right? The one is what? Sine. And what's the other one? Cosine, right? So here's theta, y, theta. You should, of course, know the graphs of these things, right? So what's sine of 0? What's cosine of 0? I heard cosine of 0 is 1. Very good. Sine of 0? 0. Let's see here. Another fun question. What if you, call this example 1. What if I wanted to solve, say, sine of theta equals to 1? Yeah. 90 degrees. So we usually work in radians in here, but 90 degrees is good for like physics and visualization. I still visualize things in degrees. Scamborda says he visualized things in radians, but I'm just not there. It's not how I was raised. But yeah, theta equals pi over 2. That's one solution. And if I was going to give you partial credit, you get 0. I mean, it's not wrong. But there's so much more, right? Like, what other solutions are there? Yeah. 5 pi over 2, still 0 partial credit, because that's the fraction of the total solutions we have. It's like 0 out of infinitely many solutions, still 0. Yeah. Sine squared plus cosine squared is 1. That's true. We'll get there. We're not there yet. What's that? Pi over 2 plus 2 pi. Ah, very good. So theta equals to pi over 2 plus 2 pi. I'm going to take that 2 pi and raise you an integer multiple of it times j, where j is an element of the integers, right? That's a fancy way of saying j is 0, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, right? Counting numbers, they're negatives and 0, integers. That notation j, that means j is an element of the integers, all right? So certainly that's one family of solutions. Totally on board with that. Let me graph it. I personally find it very insightful when I'm asked a question like this. And to be fair to you, it depends on the context. Your answer of pi over 2 or 90 degrees might have been right. It depends on how the question's asked. If I say, find all solutions, find all theta in the reals such that the above holds, such that sine theta equals to 1, well then, pi over 2 is just the start of the story, right? There's so much more. Here's how I look at it. This is sine, right? So I think of it in terms of intersection of graphs, personally. This is the one you gave me, 90 degrees. And here's the other one. Let's see here if I could graph worth anything. Sad. So is that everything? But my question is this all of them? I think it is, because we got lucky here, right? Like this and this is pi over 2, right? This is pi over 2 minus 2 pi. That's 3 pi over 2. Excuse me, minus 3 pi over 2. And so forth, right? So, in fact, we could put a box around it. Like, this is all the solutions, right? That's it. That's the entire solution set. What happens if we make it a half instead of 1, though? What happens if you try to solve, like, let's do cosine instead. What if I said cosine of theta equals to 1/2, find all solutions? How would you handle such a question? I mean, if you're starting to get my method, I think you know what I'm going to do. I'm going to say, well, I'm going to look at the graph. Cosine looks something like this, right? And the graph really just guides my thinking. It helps me make sure I'm not missing anything. But what's 1/2 look like? It's a horizontal line, right? And so you can start visualizing the solution set from the intersections of these two, right? Now, if you stick it in your calculator, what's cosine inverse of 1/2 going to give you? Yeah, square root of pi over 3. Yes, pi over 3 would be right, or 60 degrees, if you like to think that way, right? Cosine of pi over 3 is 1/2. But that was, and so there's this 2 pi periodicity of cosine, right? I mean, the fundamental things we're using, one of the things, is the 2 pi periodicity, right? What does that say? We have sine of theta plus 2 pi times j is equal to what? And the cosine of theta plus 2 pi j is what? Where j is an integer. If I go forward any multiple of cycles for sine or cosine, I'm right back where I started again, right? So I can just say sine theta and cosine theta here. I mean, these are fundamental truths about sine and cosine which help us understand their values. That always loop back any multiple of cycles. So certainly, using the 2 pi periodicity, this is the pi over 3, right? This, if I add 2 pi, where does it take me? I say pi over 3, I write pi over 2. Good job. Let's see here. Okay, how many thirds is 2 pi? 2 is how many thirds? It matters, I know, right? So 6 plus 1 is 7. 7 pi over 3, yeah? And so forth, right? The next one would be what? Plus 6, 13 pi over 3. There's this infinite family of solutions like that. But what else is there? Like, what's the other, let me do a different color. What's the other family of solutions? Yeah? Minus pi over 3. How did you know that? What's the other important properties of sine, like basic properties of sine and cosine? How about this? Sine of minus theta is what? Cosine of minus theta is what? Negative sine theta, very good. And why do we, can you put into words what these properties we just exhibited are? Sine is blank, cosine is blank. Fill in the blanks. You guys know this. Sine is odd. Cosine is even, right, yeah. So the fact that cosine is even tells me that cosine of minus pi over 3 is equal to cosine of pi over 3, right? And so when I solve this, my solution set is basically, it is something like pi over 2 plus 2 pi j, such that j is an integer, union with minus pi over 2 plus 2 pi, let's say k, such that k is an integer. There's these two infinite families that together give you the entire solution set. Right. I'm probably not telling you anything new, but I'm probably saying it in a new way, right? I mean, usually, like a lot of time in trigonometry, they'll say something like, find all the solutions from 0 to 8 pi or something like that, right? Because they don't want to face the music of describing things in terms of an integer, right? But for us, describing full solution sets in terms of an integer is at times important. That's why I'm introducing it here. Honestly, it will be a little bit until we get back to that, all right? Okay. I can't give you a full course in trigonometry. I'm just trying to hit some high points and share with you some ideas that you may or may not have seen in your course, previous coursework, all right? So let's turn the page here. The next thing is identities. What are important identities that we know for trigonometric functions? Can you guys tell me? I mean, one of you told me already. I'll write down the one you told me already. The beloved Pythagorean identity, right? Cosine squared plus sine squared theta equals to 1, right? What else do we know? How about you divide that equation by sine squared, what does it tell you?
So 1 plus cotangent squared equals
Cosecant squared theta. Now, by the way, cotangent theta is what? Cosecant theta is what? Cotangent is cosine theta over sine theta, right? Cosecant is cos theta, sorry. Cosecant theta is 1 over sine theta, right? What happens if you take the Pythagorean identity and divide by cosine squared instead of dividing by sine squared? We get what? Tangent squared, 1 secant squared theta, right? So we need, oh, by the way, secant theta is what? 1 over cos theta, right? All right. I guess I should probably tell you what tangent theta is, but you already know, right? Tangent theta is? Yeah, sine theta over cosine theta. Very good. All right, this is basic stuff. What's the next level of trig identities? Yeah?
Cosh 2x minus sinh 2x equals 1.
We don't know. We have yet to bridge the hyperbolic divide. I have not introduced the hyperbolic sine and cosine yet. You are right that almost everything I'm saying here will have a hyperbolic analog, but you're doing time travel. Hopefully about a half hour, but it depends. I love trigonometry. I can blather on about it forever, so we have to be careful, you know. The sine of 2 theta, right? Those. How about cosine squared theta is what? Sine squared theta is what? in terms of theta, or well, 1/2, 1 plus cosine 2 theta, right? This is the half angle identity. Sine squared theta is 1/2, 1 minus the cosine of 2 theta. These are pretty well-known trig identities. There's one that if you say, what happens if we do 2 times sine theta cosine theta? What's that give us?
Isn't it sine of 2 theta?
Yeah, perfect. Yeah, sine of 2 theta. Now, where did you see that before? Calc 1? Okay. First place I saw it was in physics, personally. We use it to derive the range equation in like college algebra-based physics. Now, these come up a fair amount in integration, right? Like, for example, you want to integrate cosine squared theta. How do you do it? Let me just pause from my trig my trig identification and do a little calculus here. Yeah?
You use the substitution.
Exactly. So integral of cosine squared theta d theta is the integral of 1/2 1 plus cosine of 2 theta d theta, right? And that is the integral of 1/2 d theta, right? Plus the integral of 1/2 the cosine of u times du over 2, right? If we let u equals to 2 theta, then d theta is du over 2. And so, what does this give us? This gives us theta over 2 minus, well, excuse me, plus 1/4 the sine of u plus a constant. And so theta over 2 plus 1/4 the sine of 2 theta plus a constant. There you go. That is the indefinite integral of cosine squared. Was there a question? Now, you might ask, do you need to write this u substitution out? No. This is calculus 2. This kind of u substitution does not need to be written out. You can do this in your head. I will do it in my head. Like, don't expect me to write this again. These I do without writing. Let me illustrate this. If I'm going to integrate e to the 3x dx, here's my work. 1/3 e to the 3x plus a constant. Right? This is such a simple u substitution. It is not worthy of our lead or ink. We use this to do that. Okay? Because this writing, what did it accomplish? A lot of writing, right? You could think through this, I argue. And also, with much writing comes much opportunity for making mistakes. There's some kind of balance you have to find between writing work and thinking. Where that right balance is depends on who you are. Of course, you have to write some work down, otherwise we just think you're copying from your neighbor, right? And we don't want that either. Okay, so trig identities are awesome in terms of allowing us to integrate things that we couldn't, like if you just try to integrate cosine squared, how would you do it? You have to guess that this function, when differentiated, gives you back cosine squared. Well, I mean, obviously, if you take the derivative of theta over 2 plus 1/4 the sine of 2 theta, the derivative of this is clearly that. No, it is not clear, right? So trig identities are important. They're your life's blood for doing certain integrals. Now, here's two big ones. The sine of theta plus beta is sine theta cosine beta plus cosine theta sine beta. This is the adding angles identity for sine. How many people already know this? Good. I mean, everyone should know this. We ask you questions, specific targeted questions in Math 128 to try to make you learn this. But if you're a savvy calculator user, you got around it. We're discovering. Oh well. How would you get the adding angles identity for cosine? Here's a neat trick for you. How about this? You just differentiate this guy, with respect to theta, what happens if you differentiate with respect to theta, holding beta fixed? You're like, I can't do that. That's partial differentiation. I have not learned that yet. And yet you know what I'm doing. Okay, so cosine of theta plus beta, right? Why? The chain rule says I should multiply by the derivative of theta plus beta, but what's the derivative of theta plus beta with respect to theta? Differentiate is just 1, right? So there's nothing to write there. What happens when I differentiate sine theta cosine beta with respect to theta? Keep differentiating. What do we get? You guys leave me hanging, aren't you? Cosine theta, cosine beta, yeah? What's the derivative of cosine with respect to theta? We get what? Minus sine theta, right? So you're like, you expect me to remember all those rules? Yeah, it's true. It's all true. I can't deny it. There you go. That's the adding angles formula for cosine. There's also an adding angles formula for tangent. How would you get that? What would tangent of theta plus beta be? Can you get, I mean, well, you just take these, right, and divide them, yeah? So this would be sine theta plus beta divided by the cosine of theta plus beta, which is what? You know, sine theta cosine beta plus cosine theta sine beta divided by cosine theta cosine beta minus sine theta sine beta. All right, at this point, I want a formula that's just in terms of tangents. How do I make those into tangents? Tangent theta, tangent beta is what I'm after. Yeah.
Can't you make that one right there, the first term, the first two terms like over each other? Can't you make that into a tangent and then make the other one into like inverse tangent, like arctan or something?
Well, but I mean, I don't know. I mean, this is a plus b over c plus d not equal to a over c plus b over d. Es no bueno. It's no allowed. Except for very special quality. You know, a and b would have to be very special. So I think I could be misconstruing what you're saying, but
What I was thinking is you take, can't you make
you know us math professors, we're very literal, and you may mean something different, but say something, and then we'll just ignore your meaning and attack over the literal, just jump on the literal meaning of whatever you said, you know? So you're maybe saying I should divide by something here?
Sine theta cosine beta over cosine, the base.
So here, let me put some words in your mouth. Divide by this, right? So what if we multiply the top and the bottom by that, yeah? The reciprocal of that, that's how we divide, right? Multiply by the reciprocal. This is only going to be valid for this if cosine if theta or beta were pi over 2, right? We'd be in trouble. Or any of the other infinite family that makes cosine 0, right? But then again, tangent has trouble there. Okay, so then what happens? This becomes 1. What happens? This sine theta over cosine sine theta sine beta over this is what? So this is 1, right? Minus, I believe, tangent theta, tangent beta, right? What happens upstairs? See what happens? The cosine beta, when you multiply this through and distribute, cosine beta and cosine beta leaves you with sine theta over cosine theta. In other words, the first term gives you tangent. And the second term gives you, tangent theta. And the second one gives you what? The cosine thetas cancel, right? And you get sine beta over cosine beta, which gives you plus tangent beta. All right. There are also adding angles formulas for like secant and cosecant. I don't know them. We could derive them. This is enough, okay? Do you guys, you can actually derive the cosine squared, sine squared, and these identities up here by looking at the adding angles formulas in the correct way, all right? Rather than do that, though, I'm going to share with you something, a bit of secret math. It really shouldn't be so secret. Euler knew it about, oh, I don't know, 350 years ago. I mean, he published books with it. It's not really a secret, but for some reason we hide it from you guys, which is most unfortunate because what I'm about to show you is a really simple technique to remember tons of trigonometric identities, right? Now the cost is a little bit of complex variables, but complex variables are something you need to know a little bit about going on anyway, so it's a win. So this is called Euler's formula. And Euler's formula says the following. It says that e to the I theta is cosine theta plus I times the sine of theta. Now there are ways of deriving this. I'll show you one of those later this semester, okay? But for now, just, if you would, please just take it in face value, okay? If you believe this, what happens if I put in minus theta? What's e to the minus theta? Minus I theta. I should replace theta with minus theta, right? What's cosine of minus theta? Cosine theta, right? Very good. What's sine of minus theta? Right, so minus I sine theta. So what happens when we, so then you can just think about adding or subtracting these two equations. What happens when you do that? Don't tell the other math professors I did this. Okay, so e to the I theta plus e to the minus I theta is what? These cancel, right? And you're just left with 2 times the cosine of theta. What happens when you subtract? We get e to the I theta minus e to the minus I theta, right? Equals what? Equals 2 times I times the sine of theta. Now this I, here, I is the square root of minus 1. It has, it's I squared, which is equal to minus 1, all right? It's the imaginary number I. So one more step, and then I have the formulas I wanted to share with you. So just divide by 2, we get this wonderful formula for cosine. Cosine theta is 1/2 of e to the I theta plus e to the minus I theta. And sine theta is what? Well, sine theta is 1 over 2i e to the I theta minus e to the minus I theta. You're like, well, you're just replacing something I understand a little bit and I forgot about with something I'm not familiar with and is useless to me. Well, that may be the case right now, but give me a minute or two and I'll show you why I'm showing you this, all right? Here's a demonstration. Suppose you were asked to integrate the sine of 2 theta times the cosine of 3 theta. How would you do it? Let's see here, where was I? This is example, I guess this is example 3, yeah. Whenever I ask a question like this, the answer is it's impossible with things you currently know. All right, I mean, that's just, it is my ninja way. All right, so, you know, whatever. we need a trigonometric identity to simplify sine and cosine into something that we can handle. These imaginary exponentials give us a clear path to doing it. Let me show you how. So we'll use this imaginary exponential technology, if you will, and I can use it to derive a trig identity. I don't have to memorize anything. I can derive nearly everything if I just remember these two fundamental things. Here's how it works. Sine 2 theta, cosine 3 theta. So what I got to do is I got to make a sort of simple algebraic substitution, replace this theta with 2 theta, right? So this is 1 over 2i e to the 2i theta minus e to the minus 2i theta. And then cosine of 3 theta, what's that? That's 1/2 e to the 3i theta plus e to the minus 3i theta, like that. All I did was I took my fundamental sine cosine formulas and I replaced theta with 2 theta or 3 theta. In words, I've converted sine and cosine to corresponding expressions in terms of what are called imaginary exponentials. Imaginary is a very unfortunate term. There's no more imaginary than the car that you parked outside or the dorm room you're going back to. I mean, they're every bit as real as 2 or 3. Anyway, so then you're like, well, I don't know how to manipulate imaginary exponentials. Yes, you do. Yes, you do. You just maybe haven't done it yet. How do you multiply e to the 2i theta times e to the 3i theta? What should that give you? E to the 5i theta. You are correct. It does work exactly like that. So the ordinary laws of exponents, guess what? Still cool for imaginary values. This can be proved carefully. And so I get e to the 5i theta. If I multiply this times that, I get minus e to the minus 5i theta. The product, let me do some color coding here. So this one times that one, oh, sorry, that's not what I want to do. This one times that one gives me it's that words. 3 minus 2 is 1, right? So e to the I theta. And then this one times that one. Minus 3 plus 2 is minus 3 plus 2 is minus 1. So e to the minus I theta, right? Now you just have to remember the bridge back to reality, so to speak. This is the bridge between real sine and cosine and imaginary exponentials. These two formulas are the bridge. So you have to go back on the bridge. So I have to rewrite this as like 1/2 of 1 over 2i e to the 5i theta minus e to the minus 5i theta minus 1/2 1 over 2i e to the I theta minus e to the minus I theta. I pulled out a minus. So, there's some algebraic insight that has to be exercised here. Once you do that, can you guys tell me what is this? What's that? Yep. Sine 5 theta and sine theta. Does everyone agree with them? I think so. So there we go. That's 1/2 the sine of 5 theta minus 1/2 the sine of theta. Well, now we're off to the races, right? Because we can use this trig identity to do the integral. Because now this sine 2 theta cosine 3 theta is actually the integral of 1/2 sine of 5 theta minus 1/2 sine of theta in disguise. And this, if I give you that as an integral, no one in here would have bat you wouldn't even think twice about doing it, right? That's easy. So the answer, 1 over 10 cosine of 5 theta plus 1/2 cosine theta. I'm missing a minus over here, plus a constant. There you go. An unwritten U substitution produced the 10th, because 5 times 2 is 10. See, so I don't have to memorize trig identities for multiplying sine and cosine of different arguments. I can derive it with imaginary exponentials if I want. Now, you don't have to do it this way. You can memorize. There are formulas for, like, if I've got sine of A times the cosine of B, you can find there's a formula, 1/2 cosine, it was like 1/2 sine of A plus B minus 1/2 sine of A minus B or something like that. I forget. Because I don't remember it, I derive it. And you can equally well derive these other things you know from memory. It is simple. It is easy to work out this identity using imaginary exponentials, for example. All of these, well, these, I don't know about these so much. Anyway, I just think it's a really neat technique. It'll also help you kind of maybe better appreciate Cauchy cinch I'm talking about here in just a minute. All right? Okay, so there is a lightning review of trigonometry. I guess the only other thing I should probably talk a minute or two about is the inverse trig functions. If you haven't looked at inverse trig functions before, you really should probably go back and read about them, ask me questions if you have them. I will do a couple of them because it's probably important to see it again just in case you haven't. I could go on about this for hours, but I really shouldn't. I've shown you enough. If you like it, you like it. If you don't, you can memorize stuff. It's up to you. So inverse trig functions are a little bit tricky, right? So let's talk about inverse tangent. So the graph of tangent is what? It's like this, right? Where's the vertical asymptotes? Pi over 2 and minus pi over 2, right? Because those are where what happens. Tangent theta is sine theta over cosine theta, right? So where cosine theta is 0, tangent's like, uh-oh. So plus or minus pi over 2 makes cosine 0. Consequently, tangent's not defined there. The inverse function to tangent is obtained how? Graphically. I mean, there's a choice that's being made here, but the standard inverse function is the inverse to this part of tangent, right? And so if I had drawn it better, it'll be a little bit more, you know, like this. It's probably too exaggerated. I don't know. I try. So there's the line y equals x, like here, right? And to obtain the inverse function, you reflect across the line y equals x, right? So in particular, that turns vertical asymptotes into horizontal asymptotes, right? So what's a vertical asymptote of pi over 2 becomes a horizontal asymptote of pi over 2 for the inverse tangent. And likewise down here. And so inverse hyperbolic tangent looks something like, I tried. I tried. It's almost successful, but if I can go down here with less clutter, it basically looks like that, right? Okay. So what's the derivative of inverse hyperbolic tangent is my next question. Can you tell me something that should be true about the derivative of inverse hyperbolic tangent? I said hyperbolic, I meant inverse tangent. Whatever, yeah.
It would be like hyperbolic secant squared. The inverse of.
Oh, no. So inverse tangent is not equal to cotangent. These are different functions. This one is minus, the derivative of this is minus cosecant squared. Totally right. But these are not the same function. This is the inverse, like tangent of inverse tangent of x is x once more. So it's the inverse with respect to function composition. This is the reciprocal. It's 1 over tangent. Yeah. Unfortunate, but I know it's inconsistent, but it's common notation. Like sine squared means sine squared. But inverse tangent actually is a function inverse. Not my notation, but you guys could use arctangent if you like that. I don't. So inverse tangent's also sometimes called atan, also known as arctan. These are all notations. Okay, so looking at this red graph, what could you tell me about the function we should find here? Anything? What kind of function is this? Is it going to have any horizontal asymptotes? Is it going to have any vertical asymptotes? Is it decreasing? Is it increasing? What do you think? If I have a function, if I have an inverse function, if the function's increasing, what can you say about the inverse function? Is it also increasing? Could you have a function which is increasing and at the same time an inverse function that's decreasing? No? How do you know it? I use a chain rule. But if I have f of f inverse of x, right, is equal to x, differentiate it. What happens when you differentiate this? You get df dx at f inverse of x, right, times the derivative with respect to x of f inverse of x. What's that equal to? What's the derivative of x? It's not, 1, right? So if your inverse function had a rate of change which was negative, the rate of change of your function at the corresponding inverse value of f inverse of x would also have to be negative, right? Minus minus gives you 1. On the other hand, if the inverse function is increasing, then the function must also be increasing at that corresponding value. You don't compare the same point. You compare x versus f inverse of x. But with the appropriate interpretation, yes, if a function's increasing, its inverse must also be increasing. If a function's decreasing, its inverse must also be decreasing, because the chain rule connects the derivatives like this. Yeah. Not every Calculus 1 instructor makes this point, so it's cool. My point to you is we should be expecting some kind of function which is what? It's got to be everywhere positive, whatever this answer we're looking for is, because this is an increasing function everywhere, right? Some of you might remember the answer, so you know that I'm right? How do we find the answer? How do we show that this is equal to 1 over 1 plus x squared? I mean, you should all know that, right? I'm trying to explain to you why that's true at the moment. Here's the usual method I use to derive it. I say, okay, I'm going to say y equals to inverse tangent of x. Okay? So that means that the tangent of y is what? So I'm deriving. Okay. So I said y equals inverse tangent of x. Tangent of y is what? X, right? Next step, we do implicit differentiation. What happens when we differentiate both sides? What's the derivative of tangent? Secant squared, all right. So I have to multiply by dy dx, though, because it's tangent of y. It's not tangent of x, right? So the chain rule says I must multiply by the derivative of the inside function, which in this case is y. So it's secant squared dy dx. The derivative of x, on the other hand, is 1. We settled that already. All right, and then so I solve for dy dx. That's after all what I'm after. What's that give me? Dy dx. 1 over secant squared. Right? Good news, we were just talking about trig identities. So we know that secant squared theta is actually what? 1 plus tangent squared, right? So that's 1 over 1 plus tangent squared y. But what's tangent y? X, right? So therefore, d dx of inverse tangent of x is equal to 1 over 1 plus x squared. There you go. Did you guys see this in Calculus 1? Who has not seen this in Calculus 1? Okay. Did you take it here? With who? Who? Okay, okay. But did you guys talk about the derivative of like inverse tangent? Okay, okay. He may have derived it a different way. There's a couple different ways to do it, but okay. So this is just my favorite way. It's mostly calculational. How about the derivative of inverse sine? Let's go through that one right quick then, and then I'll start talking about the hyperbolics for you guys. So how do we find, what does inverse sine look like? What is the derivative with respect to x of inverse sine of x? Here's how I work it out. I say, okay, y equals inverse sine. So sine of y is equal to x. Differentiate, what do we got? Cosine of y dy dx equals to 1, right? Now, there's a question here. When I say inverse, what do we mean by inverse sine of x anyway, guys? Like, is there an inverse function for sine? What's sine look like? Does sine pass the horizontal line test? Oh no, certainly not. It fails pretty miserably. So it's not 1-to-1, right? It doesn't output each value just once. In fact, it hits a given y value a bunch of times, right? But in order for a function to have an inverse, it has to be 1-to-1. So what does this inverse sine mean? Inverse of what function? It's not the inverse of sine, actually. Yeah.
You only evaluate it from like maybe 1-to-1 or whatever you want.
Okay.
You only evaluate a small part of it.
Right. So it's actually the inverse of just this piece of the sine function, right? So to be more obnoxious, we really should say something like this. Inverse sine is actually sine restricted to minus pi over 2 to pi over 2 inverse. So if you take a function and you cut down its domain, you make the domain smaller, you just draw a vertical bar with the new domain. This is called the restriction of a function. All right? It's kind of like being grounded. Like you used to be able to play outside. Your parents, maybe they restricted you to your room, you know, like that. I'm sorry, is it too far in your past? No, okay. It's like curfew, I don't know, whatever. So, but of course, this is like annoying and a lot to write, so we just write that instead. And it's understood that it's actually just a local inverse. Okay, that becomes important, right? Because if the inverse sine was built on this branch, this piece of sine over here, what could you say? Well, over here sine is decreasing, right? But the part we define the inverse sine to be the inverse of is where sine is increasing. Okay, that becomes important because we're going to have to make a sign choice. Pun partly intended, but like SIGN. Okay, dy dx, sorry, I'm an idiot. 1 over cosine y, you already knew that. You're still here. Let's see here. How many will withdraw after today? That's the question. This is actually slightly atypical. Like my worst lectures are my review lectures, I guarantee you. You can look ahead from previous years and see I do mellow eventually a little bit. I find this lecture very stressful. I'm trying to explain like whole courses to you and I don't, anyway. 1 over cosine y. I use this guy. See, cosine squared y, right, is 1 minus sine squared y, right? Which means that cosine of y is plus or minus the square root of 1 minus x squared. Because cosine y is x, sine y is x. So this, algebraically, is plus or minus 1 over the square root of 1 minus x squared, right? But inverse of what? It's the inverse of the part of sine which is increasing, right? So which do we choose, plus or minus? We choose the plus. But there is a thought that has to happen there, yeah? So there you go. There's the derivative of inverse sine and the derivative of inverse tangent. Now these are important, of course, because we face integrals that are based on them. If you don't know about them, it makes it like way, way harder. Let me show you a couple of integrals that are entirely based on knowledge of inverse trig derivatives. All right? And a little bit of u substitution just to make it more interesting. Example, oh, I should have given these numbers. Where was I? This was example 6? Is that right? I can't count. Example 7? It's kind of right. I mean, I might have missed one. So sorry. You guys can correct me, but now you can't because you lost your chance. Example 8. How about this? Integral of e to the x over the square root of 1 minus e to the 2x dx. It's actually kind of obvious what to do. Here's another one, example 9. Integral of sine of x dx over 1 plus the cosine squared of x. This is actually the problem with your book, by the way. All of the homework problems are very much tied to the sections which they're born of. It doesn't give you enough experience with working problems which are detached from that particular section of the book. It's almost as important to understand which kind of technique you should use as it is to implement a technique. So like your book, through its structure, has this habit of tricking you into thinking you're better than you are because you can work the problems from that section, in that section, right? That's very different than going to a test, be given the list of integrals, and just doing them, right? Because you have to sort through those integrals and go, oh, that one's integration by parts. That one's a u substitution. That one's partial fractions. That one's trig substitution, you know? These things may not make sense to you yet. In a few weeks, they hopefully will. It's just something to watch out for as you're working through the book. Try to ask yourself the question, what if this problem wasn't in this section? How would I know that's the technique I should be using on that problem? So my reason for saying that is here it should be pretty easy to do these because we just had this conversation about this and that. So you might guess what we should do. Can you see the pattern? What if I let u equal e to the x? What's du? E to the x dx, right? So this is the integral of what? Du over the square root of 1 minus, what's e to the 2x, by the way? Algebra. This is e to the x, quantity squared, right? Laws of exponents. Got to know them. Du over square root of 1 minus, aha! Look at that. If working backwards, right, is what we do. So this is inverse sine of u plus a constant. And then, of course, unsubstituting inverse sine of e to the x plus a constant. There we go. Man, see, I should have done math yesterday. I'm sorry, you guys. Yesterday, I still feel bad about it. Complete day of non-math. So stupid. All right. How about that one? What should I make u? What do you say? Sine. I thought you said 7. I had this problem with a student in a previous class. Whenever I asked for a variable name, he would say 7. He insisted that 7 should be a variable. I got very tired of it. He kept it up for a whole semester. Yeah? But you said sine? Yeah.
Maybe cosine and like bring out a negative?
Cosine and bring out a negative. Oh, sure. How about u? Yeah, so u equals cosine. If we do that, then du it's minus sine x dx, but minuses don't bother us. So that's a minus d.